We thought we understood cosmic expansion as a gradual, decelerating process. We measured galaxies receding from each other following the Big Bang's initial impulse, with gravity slowly working to pull everything back together, or at least slow the expansion rate. The universe seemed destined either to collapse back in a big crunch or to expand forever while gradually approaching a static state. We discovered something far more disturbing. In 1998, observations of distant supernovae revealed that the universe's expansion is accelerating rather than decelerating. Galaxies aren't just moving apart, they're moving apart faster over time. Something with negative pressure, dubbed dark energy, permeates all space and drives acceleration against gravity's attractive pull. This dark energy comprises approximately 68% of the universe's total energy content, dominating cosmic evolution and determining the universe's ultimate fate. Webb's observations have provided the most precise measurements yet of how this acceleration varies with cosmic time. By observing distant galaxies whose light has traveled billions of years to reach us, Webb maps the universe's expansion history with unprecedented detail. The data reveals subtle variations in expansion rate across different epochs, constraining models of dark energy and testing whether its strength changes over time. The most unsettling possibility appears in certain theoretical models where dark energy strengthens over time rather than remaining constant. If dark energy's negative pressure becomes increasingly negative, a scenario called phantom energy, the expansion acceleration would increase without bound. Eventually, expansion would accelerate so dramatically that it overcomes not just gravity holding galaxies together, but electromagnetic forces binding atoms and even nuclear forces binding atomic nuclei. Scientists analyzing Webb's distance measurements and galaxy recession velocities throughout 2023 and 2024 found data consistent with dark energy remaining approximately constant, but unable to definitively rule out models where it slowly strengthens. The precision of measurements improved dramatically over previous observations from Hubble and ground-based telescopes, yet the fundamental question remains unresolved. Is dark energy truly constant, or does it evolve toward the phantom regime that would tear the universe apart? Dr. Adam Rees, who shared the 2011 Nobel Prize in Physics for discovering cosmic acceleration through supernova observations, emphasized that understanding dark energy's nature represents the most pressing question in cosmology. Webb's capabilities to observe extremely distant galaxies and measure their properties with exceptional precision provide crucial data for distinguishing between models that predict stable, eternal expansion versus catastrophic Big Rip scenarios. This exploration will take us from the foundations of cosmic expansion through the discovery of acceleration, from Webb's observational techniques to theoretical frameworks describing dark energy. We'll examine how measurements of distant objects constrain expansion history, what different dark energy models predict for the universe's fate, and how soon, if ever, a Big Rip might occur. We'll discover that the universe's future depends on the equation of state parameter W that quantifies dark energy's pressure relative to its density. If you're fascinated by discoveries suggesting the cosmos might be evolving toward its own destruction, subscribe and give this video a thumbs up. And consider this: if space itself can stretch and potentially tear, what does that reveal about the nature of the vacuum, the stability of physical law, and whether our universe represents merely one bubble in an eternally inflating multiverse? Comment your thoughts. I'll pin the most insightful response. For most of human history, the universe appeared static and eternal. Stars moved in regular patterns, but the overall cosmic structure seemed unchanging. This assumption dominated cosmology until the early 20th century, when observations began revealing that the universe evolves dynamically rather than remaining forever constant. Einstein's general theory of relativity, completed in 1915, provided the mathematical framework for describing how space-time responds to matter and energy. When Einstein applied his equations to cosmology, he found they predicted a dynamic universe, either expanding or contracting, not the static cosmos he expected. To force a static solution, Einstein added a cosmological constant to his equations representing a repulsive force that could balance gravity's attraction. The cosmological constant introduced energy density intrinsic to space-time itself, rather than associated with matter or radiation. This vacuum energy would exert negative pressure, pushing space apart rather than pulling it together. Einstein later called this his greatest blunder after Edwin Hubble's observations in 1929 demonstrated that the universe actually expands, eliminating the need for a cosmological constant to maintain static solutions. Hubble discovered that distant galaxies show redshifts in their spectral lines proportional to their distances. Galaxies farther away recede faster. This relationship, now called Hubble's law, provided the first clear evidence that space itself expands, carrying galaxies apart. The proportionality between distance and recession velocity indicated uniform expansion where every region of space stretches at the same rate. The Big Bang theory emerged from extrapolating this expansion backward in time. If space currently expands, it must have been denser and hotter in the past. Following this logic to its extreme suggests the universe originated approximately 13.8 billion years ago from an extremely hot, dense state, and has been expanding and cooling ever since. For decades, cosmologists debated whether the universe would expand forever or eventually recollapse. The answer depended on the universe's total density. If matter density exceeded a critical value, gravity would eventually halt expansion and reverse it, leading to a big crunch. If density fell below critical, expansion would continue forever. The boundary case, exactly critical density, would produce expansion that gradually slows towards zero rate asymptotically. Measurements throughout the late 20th century suggested the universe possessed approximately critical density, but detailed observations of expansion rate over cosmic time would determine the precise fate. The expected behavior in all scenarios involved deceleration. Gravity should slow expansion regardless of whether it eventually reverses. The 1998 discovery that expansion accelerates rather than decelerates shocked the cosmology community. Two independent teams observing distant type Ia supernovae found that these objects appeared fainter than expected for their measured redshifts, indicating they lie farther away than models with decelerating expansion predicted. The most natural explanation involved accelerating expansion where space stretches at increasing rates. This acceleration requires something with negative pressure permeating space, pushing it apart against gravity. Einstein's cosmological constant, dismissed for decades after Hubble's discovery, returned as the simplest explanation. Alternatively, some dynamic field called quintessence might drive acceleration. Both possibilities fall under the umbrella term dark energy, referring to whatever causes cosmic acceleration. Three major revelations emerge from Webb's observations. First, the acceleration appears consistent with a cosmological constant to current measurement precision, but phantom energy models where acceleration intensifies remain possible. Second, the expansion history constrains dark energy's equation of state parameter to within a few percent of W summation 1, the value corresponding to a cosmological constant. Third, if phantom energy exists with W1, the Big Rip could occur within approximately 100 billion years, though uncertainties remain large. Now let's begin by establishing the foundations of cosmic expansion and understanding how space itself can stretch, carrying galaxies apart. Cosmic expansion. The expansion of the universe represents one of the most profound discoveries in science. Space itself stretches, carrying galaxies apart without any center or edge to the expansion. Understanding this requires abandoning intuitive pictures of explosions in space and embracing the geometric concept of space expanding everywhere simultaneously. The expansion follows from general relativity applied to a homogeneous, isotropic universe described by the Friedmann equations. Homogeneity means the universe appears the same at every location on sufficiently large scales. While galaxies cluster into groups, clusters, and larger structures locally, averaging over regions spanning hundreds of millions of light-years reveals uniform matter distribution. Observations confirm this statistical homogeneity through galaxy surveys and cosmic microwave background measurements, showing the same properties in all directions. Isotropy means the universe appears the same in all directions from any given location. We observe no preferred direction. The cosmic microwave background shows nearly identical temperature in all directions after accounting for small fluctuations. Galaxies at any particular distance show similar properties regardless of which direction we look. This isotropy applies to all observers, not just Earth-based humans. The cosmological principle combines homogeneity and isotropy, stating that on large scales, the universe possesses no special locations or directions. This principle, while an assumption rather than a derived result, receives strong observational support and dramatically simplifies cosmological modeling. A homogeneous, isotropic universe admits simple solutions to Einstein's field equations, called Friedmann-Lemaitre-Robertson-Walker (FLRW) metrics. The FLRW metric describes spacetime geometry through a scale factor, AT, that characterizes how distances between co-moving points change over time. Co-moving coordinates remain fixed for observers following the cosmic expansion. Galaxies at rest, relative to the cosmic microwave background, maintain constant co-moving coordinates, while their physical separation increases as AT grows. The physical distance between co-moving points equals the scale factor times the co-moving distance. If two galaxies are separated by co-moving distance, hg, their physical separation equals d eats AT. As the scale factor increases, physical distances grow proportionally while co-moving distances remain constant. This captures how space expands, carrying galaxies apart. The Hubble parameter, ht, seed AA, where A represents the time derivative of the scale factor, quantifies the expansion rate at time t. The Hubble constant h0 denotes the current expansion rate, measured to be approximately 70 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years of separation, galaxies recede at 70 kilometers faster velocity. Hubble's law, v(h0d), relates recession velocity v to distance d through the Hubble constant. Distant galaxies recede faster than nearby galaxies because more intervening space expands between us and them. This doesn't mean galaxies move through space at high velocities, but rather that space itself expands, increasing distances. The cosmic redshift provides the observable manifestation of expansion. Light traveling from distant galaxies gets stretched as space expands during its journey to Earth. Wavelengths increase proportionally to the scale factor, shifting spectral features toward longer wavelengths. The redshift z relates to scale factor through 1 plus house A0 ka emit, where A0 represents current scale factor and AI emit the scale factor when light was emitted. For nearby galaxies with small redshifts, ZVC, where V equals recession velocity and C denotes light speed. This allows determining velocities from measured redshifts. For distant galaxies with large redshifts approaching or exceeding Z-1, the relationship becomes more complex and must account for relativistic effects and expansion history. The expansion rate varies over cosmic time according to the Friedmann equation, the fundamental differential equation governing scale factor evolution. The equation relates the square of h to matter density, radiation density, curvature, and any cosmological constant or dark energy. The relative contributions of these components change as the universe expands, affecting how expansion rate evolves. In the early universe, radiation dominated the energy density. Radiation density decreases as A4 as space expands because both photon number density and individual photon energy decrease. During this radiation-dominated epoch, expansion decelerated with scale factor growing as a T1.2, where T represents time since the Big Bang. As the universe expanded and cooled, matter density eventually exceeded radiation density. Matter density decreases as A3 as space expands, since mass remains constant, while volume increases. During matter domination, expansion continued decelerating but more slowly than during radiation domination, with scale factor evolving as a T2-3. Throughout these epochs, expansion decelerated because gravity worked to pull matter together, slowing the expansion rate over time. The deceleration parameter, QCXA2, quantified this, with positive values indicating deceleration. Standard Big Bang models predicted Q should equal 0.5 during matter domination, assuming no cosmological constant. The discovery of cosmic acceleration revealed that currently, expansion accelerates rather than decelerates, implying negative deceleration parameter Q 0.5p5. This acceleration began relatively recently in cosmic history, when dark energy density became comparable to matter density. Earlier epochs still experienced deceleration as expected from gravitational effects of matter and radiation. Dark energy density remains constant as space expands if it behaves as a cosmological constant. While matter density dilutes as A3 and radiation as A4, cosmological constant energy density stays fixed. Initially negligible compared to matter and radiation densities, dark energy gradually became significant as those components diluted, eventually dominating and driving accelerating expansion. The critical density Ri crit, Ohad 3H2 8pg, determines whether spatial geometry is flat, open, or closed. Current measurements indicate the universe possesses very nearly critical density with total R total or R crit WAST 1.0 within measurement uncertainties. This implies flat spatial geometry where parallel lines never converge or diverge, and the universe extends infinitely in all directions. The energy budget breaks down as approximately 68% dark energy, 27% dark matter, and 5% ordinary matter. Dark matter interacts gravitationally but not electromagnetically, making it invisible except through gravitational effects on visible matter and light. Its presence is inferred from galaxy rotation curves, gravitational lensing, and cosmic structure formation. Ordinary matter comprises everything made of atoms, stars, planets, gas, dust, and living organisms. The expansion occurs everywhere simultaneously with no center or edge. Every observer sees all others receding according to Hubble's law. This can seem paradoxical. How can everyone recede from everyone else? The resolution involves recognizing that space itself expands rather than galaxies moving through static space. On a grid drawn on an expanding balloon surface, every point sees all other points recede with velocities proportional to distance. Galaxies beyond certain distances recede faster than light speed due to expansion of intervening space. This doesn't violate relativity's prohibition on faster-than-light motion through space because galaxies remain essentially at rest in their local regions while space between expands. Objects can separate faster than light through expansion of intervening space, even though nothing moves faster than light through space locally. The observable universe contains only regions from which light has had time to reach us since the Big Bang. This creates a cosmic horizon approximately 46 billion light-years away in co-moving distance, despite the universe being only 13.8 billion years old, because space has expanded during light's travel time. Regions beyond this horizon remain forever causally disconnected. We cannot see them or receive signals from them. Understanding cosmic expansion as space itself stretching provides the framework for examining how acceleration affects this process, and what observations reveal about whether expansion might accelerate indefinitely or even intensify toward catastrophic endpoints. Dark energy discovery. The 1998 discovery of cosmic acceleration through observations of distant Type Ia supernovae revolutionized cosmology by revealing that approximately 68% of the universe consists of mysterious dark energy driving expansion to accelerate against gravity. Understanding this discovery requires examining how Type Ia supernovae serve as standardizable candles for measuring cosmic distances and how their unexpected dimness revealed accelerating expansion. Type Ia supernovae occur when white dwarf stars in binary systems accrete mass from companions until reaching the Chandrasekhar limit near 1.4 solar masses, triggering thermonuclear explosions that destroy the white dwarf completely. The explosion mechanism, runaway fusion of carbon and oxygen under degenerate conditions, produces remarkably consistent peak luminosities, making these supernovae valuable distance indicators. The physics underlying this consistency involves the white dwarf's degenerate equation of state of electron degeneracy pressure supporting the white dwarf depends on density alone, not temperature. This creates a stable configuration until mass approaches the Chandrasekhar limit, where pressure can no longer support the star against gravity. Collapse heats the interior, igniting carbon fusion that runs away because degeneracy pressure doesn't increase with temperature. The thermonuclear flame propagates through the white dwarf in seconds, completely disrupting the star and synthesizing approximately 0.5 to 1 solar mass of radioactive nickel-56. This nickel-56 decays to cobalt-56 with 6.1-day half-life, then to stable iron-56 with 77-day half-life. The decay energy powers the supernova light curve, creating the characteristic rise to peak luminosity over approximately 2 weeks, followed by exponential decline over months. Because the explosion mechanism and fuel mass remain relatively consistent across Type Ia supernovae, peak luminosities cluster tightly around an average value approximately 5 billion times the Sun's luminosity. Small variations in peak brightness correlate with light curve shape. Brighter supernovae decay more slowly, dimmer ones faster. This relationship, discovered empirically and understood theoretically through models of nickel mass and expansion dynamics, allows standardizing peak luminosities. After correcting for light curve shape, Type Ia supernovae serve as standard candles with known intrinsic luminosity. Comparing intrinsic luminosity to observed apparent brightness determines distance through the inverse square law. Apparent brightness decreases as the square of distance. This technique, called luminosity distance measurement, provides accurate distances to supernovae occurring in galaxies billions of light years away. Measuring redshifts from supernova host galaxy spectra gives recession velocities, or more precisely, how much space has expanded since light was emitted. Combining distance and redshift measurements maps the expansion history, how far light traveled versus how much expansion occurred during its journey. This relationship depends on expansion rate's evolution over cosmic time, constraining cosmological models. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, independently conducted surveys discovering dozens of distant Type Ia supernovae at redshifts 0.3 to 1.0. These supernovae occurred when the universe was 40% to 70% its current age, allowing tests of whether expansion decelerated as expected from gravity-slowing expansion. The surprising result showed supernovae appearing fainter than expected for their measured redshifts. If expansion had decelerated as predicted by models containing only matter and radiation, supernovae at given redshift would lie closer and appear brighter. The observed dimness indicated supernovae lie farther away, requiring accelerating expansion, where space stretched faster recently than in the past. Quantitatively, the best fit to data required negative deceleration parameter, Q, 0.55, indicating acceleration rather than deceleration. This implied that some component with negative pressure, now called dark energy, dominates the universe's energy budget and drives accelerating expansion. The result contradicted theoretical expectations but followed rigorously from observations. The statistical significance of the discovery reached high confidence levels. With dozens of supernovae showing consistent dimming beyond expectations, the probability that random fluctuations produced the signal approached negligibly small values. Independent confirmation from two teams using different telescopes, reduction pipelines, and analysis techniques strengthened confidence that the result represented genuine cosmic acceleration rather than systematic errors. Potential systematic uncertainties required careful examination. Could dust absorption in host galaxies or intervening space-dim supernovae mimicking apparent dimness from acceleration? Dust absorption preferentially affects blue light, creating reddening that spectra can detect and correct for. Analysis showed dust couldn't explain the full dimming without producing reddening larger than observed. Could type Ia supernovae at high redshift differ intrinsically from nearby ones, perhaps exploding with lower luminosities billions of years ago? This seemed unlikely given the robust physics of Chandrasekhar mass white dwarf explosions, but required checking. Detailed studies of supernova spectra, light curves, and correlations found no evidence for systematic evolution. High redshift supernovae, after standardization, matched nearby ones' properties. Could gravitational lensing by intervening matter magnify nearby supernovae preferentially, making distant ones appear relatively dim? Lensing effects average nearly neutral over large samples and would produce scatter increasing with distance rather than systematic dimming. The observed effect showed systematic shifts inconsistent with lensing explanations. The cosmological constant provided the simplest explanation for accelerating expansion. Einstein's equations naturally accommodate a constant vacuum energy density with equation of state parameter W stood PRC2 as to 1, where P represents pressure and R energy density. Negative pressure W shucked to 1 drives acceleration, with magnitude set by the cosmological constant L. The required cosmological constant value, approximately L1.1 x 10^52 per meter squared, produces energy density OL 0.7 in units of critical density. This matches the approximately 68–70% dark energy fraction inferred from supernova data, combined with cosmic microwave background measurements constraining total density to near critical value, or Y total 1. Alternative models proposed dynamical dark energy fields called quintessence, where energy density and equation of state parameter vary over cosmic time rather than remaining constant. These models introduce scalar fields rolling down potential energy landscapes, with dynamics determining how dark energy evolves. Different potentials produce different expansion histories, testable through precise measurements of acceleration over cosmic time. The 2011 Nobel Prize in Physics, awarded to Perlmutter, Schmidt, and Rees, recognized the discovery's profound implications. Cosmic acceleration demonstrated that the universe's fate involves accelerating expansion rather than eventual recollapse or simple coasting. Dark energy's dominance determines cosmic evolution for the infinite future, affecting structure formation, galaxy evolution, and the ultimate disposition of all matter and energy. Subsequent observations confirmed and refined the discovery. Ground-based telescopes and the Hubble Space Telescope observed hundreds of additional Type Ia supernovae at various redshifts, mapping expansion history with increasing precision. Cosmic microwave background measurements from WMAP and Planck satellites provided independent evidence for dark energy through constraints on spatial curvature and total energy density. Baryon acoustic oscillations, characteristic scales imprinted in galaxy distributions by sound waves in the early universe, offered another independent probe of expansion history. These scales evolved predictably with expansion, providing standard rulers complementing supernova standard candles. Measurements confirmed accelerating expansion and dark energy dominance. The concordance LCDM model emerged as the standard cosmological framework. LCDM combines a cosmological constant L, driving acceleration with cold, dark matter CDM, providing gravitational scaffolding for structure formation. This 6-parameter model fits diverse observations from cosmic microwave background through large-scale structure to supernova distances with remarkable consistency. Despite empirical success, dark energy's nature remains mysterious. Why does vacuum energy possess the particular small but non-zero value observed, rather than zero or enormous values quantum field theory naively suggests? This cosmological constant problem represents one of physics' deepest puzzles. Attempts to calculate vacuum energy from quantum fields typically yield results 120 orders of magnitude too large. The coincidence problem asks why dark energy density and matter density have similar magnitudes today after evolving differently throughout cosmic history. Matter density decreased from dominant to subdominant as expansion diluted it, while dark energy density remained constant. Why do we observe the universe during the brief cosmic epoch when both have comparable densities? Understanding dark energy's discovery establishes the empirical foundation for examining Webb's new observations, testing whether dark energy remains constant or evolves, and whether acceleration might intensify toward catastrophic scenarios. Webb's observations, the James Webb Space Telescope's infrared capabilities enable observations of extremely distant galaxies whose light has traveled more than 13 billion years to reach us, providing unprecedented data on cosmic expansion history across most of the universe's lifetime. Webb's observations constrain dark energy's properties by measuring distances to and redshifts of galaxies at various cosmic epochs, testing whether expansion acceleration remains constant or varies over time. Webb's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, observe wavelengths from 0.6 to 28 microns, ideal for detecting high redshift galaxies whose ultraviolet and optical light has been redshifted into infrared wavelengths by cosmic expansion. A galaxy emitting light when the universe was only 500 million years old, corresponding to redshift Z10, shows its ultraviolet emission shifted to near-infrared wavelengths around 1.3 microns. Webb's 6.5-meter primary mirror collects significantly more light than Hubble's 2.4-meter mirror, providing approximately 7 times greater collecting area. This increased light-gathering power enables detection of fainter objects in shorter exposure times or brighter detection of known objects, allowing detailed spectroscopy. The improved sensitivity reveals galaxies at redshifts Z10 that remained beyond Hubble's reach. Deep field observations targeting small sky regions with long exposure times accumulate photons from extremely faint distant galaxies. Webb's JWST Advanced Deep Extragalactic Survey (JDES) program observed regions near the Hubble Ultra Deep Field, discovering galaxies at redshifts exceeding Z-13, corresponding to when the universe was only 300 million years old. These observations probe earlier cosmic epochs than previously accessible. Spectroscopic measurements using Webb's NIR-SPEC instrument disperse galaxy light into spectra revealing emission and absorption lines from hydrogen, oxygen, and other elements. Measuring these lines' wavelengths determines precise redshifts through the ratio of observed to rest frame wavelength. Spectroscopic redshifts provide higher accuracy than photometric redshifts estimated from broadband colors. Distance measurements combine multiple techniques. The luminosity distance inferred from object brightness assumes known intrinsic luminosity. For galaxies at redshifts z-1, type Ia supernovae become rare and difficult to detect, requiring alternative distance indicators. Webb observes Cepheid variable stars in galaxies hosting recent supernovae, calibrating supernova luminosities by measuring distances through Cepheid period luminosity relations. Gravitational lensing by foreground galaxy clusters magnifies background galaxies, allowing Webb to observe objects too faint for direct detection. The magnification factor, determined from lens mass distribution modeling, converts observed brightness to intrinsic brightness, enabling distance inference. Multiple images of the same background galaxy provide redundant distance measurements testing consistency. The tip of the red giant branch, TRGB, the luminosity of stars at a specific evolutionary stage, serves as another distance indicator. Red giant stars reach maximum luminosity at the TRGB before helium flash, providing a standard candle with well-calibrated absolute magnitude. Webb resolves individual TRGB stars in galaxies to distances exceeding 100 million light-years, extending this technique's range. Surface brightness fluctuations in elliptical galaxies provide distances through the relationship between pixel-to-pixel brightness variations and distance. Nearby galaxies show larger fluctuations because individual stars are resolved, while distant galaxies show smoother brightness as stars blend together. Webb's sharp imaging and infrared wavelengths, where old stars dominate, enable TRGB and surface brightness fluctuation measurements to unprecedented distances. Combining distance and redshift measurements from objects at various cosmic epochs constrains expansion history. The relationship between luminosity distance and redshift depends on how expansion rate evolved over cosmic time. Models with different dark energy properties predict different distance-redshift relationships, allowing observations to discriminate among possibilities. The equation of state parameter W/P RC2 characterizes dark energy's properties. For a cosmological constant, W/1 exactly. For quintessence fields, W might differ from 1 and possibly vary with time. Phantom energy models have W1 producing stronger acceleration than a cosmological constant. Measuring W and its potential time variation tests dark energy's nature. Webb observations through 2023-2024 measured distances to galaxies and supernovae across redshifts, Z/0.5 to Z/9, covering cosmic times from 13 billion years ago to relatively recent epochs. Statistical analysis of hundreds of distance measurements constrains W to approximately W/103 plus 0.06, consistent with cosmological constant, but allowing modest deviations. The time variation of W, parameterized as WA, or W0 plus WA and 1A, where A represents scale factor, remains poorly constrained. Current data allows WA ranging from approximately 0.5 to plus 0.5, indicating that dark energy might strengthen, weaken, or remain constant over cosmic time. Webb's measurements improve constraints compared to previous datasets, but haven't definitively detected evolution. Tension between measurements of the current expansion rate, H0, from different methods, creates uncertainty affecting dark energy constraints. Local measurements using Cepheids and supernovae yield H0 73 km SMPC, while cosmic microwave background measurements assuming LCDM give H0 67 km SMPC. This approximately 9% discrepancy, persisting despite improved observations, suggests either systematic errors or new physics. Webb observations aim to resolve this Hubble tension by providing independent distance measurements with different systematic uncertainties than previous work. Early results show distances consistent with local measurements supporting higher H0 values, but analysis continues and final conclusions await completed surveys. If tension persists in Webb data, explanations might require modifying LCDM through evolving dark energy, additional relativistic species, or other exotic physics. Systematic uncertainties affecting distance measurements require careful treatment. Dust extinction dims objects, requiring correction through observed colors and spectral features. Gravitational lensing by intervening structure magnifies or demagnifies objects, statistically averaging to small effects, but creating scatter. Peculiar velocities from local gravitational infall add non-cosmological redshift components requiring subtraction. The cosmic microwave background provides complementary constraints on dark energy through measurements of spatial curvature, matter density, and acoustic peak structure. Planck satellite observations combined with Webb galaxy data improve constraints on W and WA by breaking degeneracies between parameters. Joint analysis of multiple datasets provides stronger constraints than any single probe. Baryon acoustic oscillations measured through galaxy clustering surveys trace expansion history through characteristic scales set in the early universe. These standard rulers complement supernova standard candles and Webb's galaxy observations. The Dark Energy Spectroscopic Instrument, DESI, survey collecting redshifts of 40 million galaxies, will provide precise BAO measurements over cosmic time. Weak gravitational lensing distorts background galaxy shapes through matter distribution along the line of sight. Statistical analysis of shape distortions probes matter clustering and expansion history. Webb's sharp imaging enables weak lensing measurements to high redshifts where previous observations struggled to detect coherent distortions. Future Webb observations will extend measurements to earlier cosmic epochs and increase sample sizes at all redshifts. Improved statistics will tighten constraints on W and WA, potentially detecting time evolution if it occurs at levels accessible to observations. The combination of multiple probes and increased precision might resolve whether dark energy remains constant or varies, and whether phantom energy threatens eventual cosmic destruction. Understanding Webb's observational techniques and current results establishes what we know about dark energy from data, while highlighting remaining uncertainties. The measurements constrain but don't yet definitively determine whether space faces accelerating expansion toward eventual tearing apart. The phantom. Menace phantom energy represents a theoretical form of dark energy with equation of state parameter W1 creating negative pressure stronger than a cosmological constant and driving expansion acceleration that intensifies over time. If phantom energy exists, the universe faces eventual catastrophic destruction in a big rip, where expansion accelerates so dramatically that it overcomes all binding forces, tearing apart galaxy clusters, galaxies, solar systems, planets, molecules, atoms, and ultimately spacetime itself. The equation of state parameter W times P, RC2, relates pressure P to energy density R. For normal matter, including dust, gas, and dark matter, W0 indicating negligible pressure compared to energy density. For radiation, W13 reflecting radiation pressure. For a cosmological constant representing constant vacuum energy density, say W equals 1 exactly. Values WL1 indicate phantom energy with pressure more negative than a cosmological constant. Phantom energy violates the weak energy condition, a technical requirement from general relativity stating that energy density R plus PC2 remains non-negative for all observers. For W1, this sum becomes negative, seemingly violating physical expectations. However, general relativity doesn't fundamentally forbid weak energy condition violations. Classical solutions with exotic matter can violate it, and quantum fields definitely can. The physics driving phantom energy could involve scalar fields with unusual kinetic energy terms in their Lagrangian densities. Standard scalar fields like those in quintessence models have positive kinetic energy. Phantom fields possess negative kinetic energy, creating instabilities at quantum level that raise theoretical concerns. Despite these worries, phantom energy remains mathematically consistent with general relativity's field equations. If dark energy possesses constant W1, expansion acceleration intensifies without bound. The acceleration parameter, AIA, increases over time rather than remaining constant as for a cosmological constant. Eventually, this acceleration becomes so extreme that it overcomes gravitational binding of structures, electromagnetic forces binding atoms, and even nuclear forces binding atomic nuclei. The Big Rip scenario proceeds through definite stages occurring at calculable times before the final singularity. Working backward from the singularity, at approximately 1 month before the Big Rip, galaxies unbind as expansion acceleration overcomes their gravitational binding. Stars fly apart as the Milky Way, and all other galaxies disintegrate. The night sky would appear increasingly empty as distant galaxies disappear beyond cosmic horizons. At approximately 3 months before the end, solar systems unbind. Planets escape stellar gravitational wells as expansion accelerates beyond binding forces. Earth would be flung from the Sun's orbit into interstellar space, though interstellar loses meaning, as space itself tears apart. At approximately 30 minutes before the singularity, planets themselves disintegrate as expansion overcomes gravitational binding holding them together. Earth would fragment into pieces flying apart at accelerating rates driven by space expansion overwhelming gravity. At approximately 10-19 seconds before the end, atoms disintegrate as expansion forces overcome electromagnetic binding between nuclei and electrons. All matter reduces to free nuclei and electrons scattered through fragmenting space. At the final moment, atomic nuclei disintegrate as expansion forces exceed strong nuclear force binding protons and neutrons. Even space-time itself faces infinite curvature singularity as expansion rate diverges. The universe ends not in fire or ice, but in violent tearing of all structure down to fundamental constituents. The time until Big Rip depends on how negative W is and on the current dark energy density. For W sub 1.5, calculations predict Big Rip occurring approximately 22 billion years from now. For W Tonka 1.1, the timescale extends to approximately 150 billion years. Current observational constraints, W 1.3 at 95% confidence, place the earliest possible Big Rip at roughly 50 billion years from now. These timescales vastly exceed human civilization's existence and even stellar lifetimes for most stars. The Sun will become a red giant consuming Earth's orbit in approximately 5 billion years, long before any Big Rip. Most stars will have exhausted their nuclear fuel before phantom energy, if it exists, tears apart galactic structures. The Big Rip represents an absolute end, a genuine singularity where physical quantities diverge and general relativity breaks down completely. Unlike black hole singularities hidden behind event horizons, the Big Rip singularity would be cosmological, affecting all space and time simultaneously. No escape routes or survival strategies exist. The singularity destroys everything. Could quantum gravity effects prevent the Big Rip by modifying physics near the singularity? This remains unknown. Quantum gravity might impose minimum length scales, preventing space-time from tearing below Planck length, or it might allow the singularity with unknown consequences. Current lack of complete quantum gravity theory prevents definitive predictions. Phantom energy faces significant theoretical objections beyond weak energy condition violation. The negative kinetic energy creates instabilities. Small perturbations grow exponentially, destabilizing the phantom field. Quantum corrections typically generate infinite vacuum energy from these instabilities, though perhaps fine-tuning or unknown symmetries could control corrections. The Big Rip scenario assumes phantom energy maintains dw1 indefinitely into the future. Alternative models propose that W crosses 1 starting above 1 in the past, equaling 1 recently, and becoming less than 1 in the future. Such crossing requires dynamical scalar fields with specific potential energy functions, adding complexity compared to simple cosmological constant models. Some quintessence models produce effectively phantom-like behavior without actual W1 through complex dynamics involving multiple fields or non-standard kinetic terms. These models might accelerate expansion dramatically while avoiding some theoretical problems of true phantom energy, though they typically require fine-tuning to match observations. The observational challenge involves measuring W precisely enough to determine whether it equals 1, exceeds 1 slightly, or falls below 1. Current measurements constrain W to approximately plus tie 0.06 around 1, insufficient to definitively exclude phantom energy. Improving constraints requires better distance measurements and larger samples across wider redshift ranges. Different observational probes provide independent constraints helping to break degeneracies. Supernovae measure luminosity distances directly. Baryon acoustic oscillations provide standard rulers. Cosmic microwave background anisotropies constrain early universe physics and expansion history. Combining all probes yields stronger constraints than any individually. Upcoming surveys, including the Vera Rubin Observatory's Legacy Survey of Space and Time, Euclid satellite observations, and Nancy Grace Roman Space Telescope measurements, will observe thousands of supernovae and millions of galaxies across cosmic time. Statistical power from these large samples should constrain W to precision approaching plus 0.02, potentially detecting deviations from W1 if they exist. If observations definitively measure W1, the implications would be profound. Theoretical physics would need explaining how phantom energy arises from fundamental principles, while managing its instabilities and energy condition violations. Cosmology would face certainty that the universe heads toward catastrophic destruction in tens to hundreds of billions of years. Alternatively, if observations confirm W1 within tightening error bars, this would support the cosmological constant interpretation and suggest the universe faces eternal, accelerating expansion without Big Rip, but still approaching empty, isolated future as all structure beyond our local gravitationally bound group recedes beyond horizons. The possibility that we live during a unique cosmic epoch when dark energy density happens to equal matter density roughly, and when W potentially crosses from above to below. One raises anthropic questions. Perhaps only universes with these special properties allow observers to exist, selecting from a multiverse landscape of possibilities. Understanding phantom energy as theoretical possibility motivates precision observations testing whether this extreme scenario represents reality or merely mathematical curiosity excluded by data. Alternative scenarios. Beyond the cosmological constant and phantom energy, theorists have proposed numerous dark energy models attempting to explain cosmic acceleration through various mechanisms. These alternatives include quintessence fields, vacuum decay, modified gravity theories, and scenarios involving extra dimensions or multiverse dynamics. Each makes different predictions for expansion history and ultimate cosmic fate, testable through precision observations. Quintessence represents the broadest class of alternatives, using dynamical scalar fields rolling down potential energy curves to drive acceleration. Unlike the cosmological constant, where vacuum energy density remains fixed, quintessence field energy density and equation of state parameter evolve over cosmic time as the field value changes. Different potential energy functions produce different evolutionary tracks. Tracker quintessence models possess potentials designed such that field dynamics track the dominant energy component, maintaining constant fraction of total density despite changing conditions. During radiation domination, quintessence constitutes a small fraction of energy density. During matter domination, it grows to eventually dominate and drive acceleration. This tracking behavior potentially explains why dark energy becomes important during the current cosmic epoch. The potential energy functions for tracker models typically involve inverse powers of the field, Vf, Fn, where n is a positive constant. As the field rolls down this potential, its energy density decreases, but at rates ensuring it remains subdominant during early epochs while becoming dominant recently. These models require fine-tuning initial conditions, but less severely than simple cosmological constant explanations. K-essence models modify kinetic terms in the scalar field Lagrangian using non-canonical kinetic energy functions that depend on field derivatives in non-standard ways. These non-canonical kinetic terms can produce accelerating expansion without requiring potential energy domination. K-essence can violate energy conditions under certain conditions, potentially producing phantom-like behavior without actual phantom energy. Coupled quintessence models introduce interactions between dark energy fields and dark matter, allowing energy transfer between these components. The coupling affects matter clustering on cosmic scales and alters expansion history in ways distinguishable from uncoupled models. Observations of large-scale structure formation constrain coupling strengths, requiring them to remain small to match observed matter distributions. Vacuum decay scenarios propose that the current vacuum state represents a false vacuum that will eventually decay to lower energy true vacuum through quantum tunneling. The decay would nucleate bubbles of true vacuum expanding at light speed, destroying the false vacuum. Inside bubbles, different physics might apply with different particle masses and force strength. This represents catastrophic scenario, possibly more sudden than Big Rip. The decay rate depends on the potential energy barrier separating false from true vacuum. High barriers produce extremely long lifetimes, vastly exceeding the current universe age. Lower barriers allow decay on cosmological timescales. Current vacuum stability remains uncertain. Standard model Higgs potential calculations suggest our vacuum might be metastable, stable against small perturbations, but potentially unstable over immense timescales. Modified gravity theories propose that general relativity itself requires alteration on cosmological scales rather than introducing dark energy as new matter component. These theories modify Einstein's equations through additional terms or different functional forms of the gravitational action. The modifications must be designed to become important only at extremely large distances, while reducing to standard general relativity locally. Fr, gravity, replaces the Einstein-Hilbert action with a function Fr of the Ricci scalar curvature R. Different functions produce different cosmological behaviors. Some Fr models can drive accelerating expansion without dark energy, though they often face theoretical problems like ghost instabilities or observational constraints from solar system tests. DGP, Diwali Gabadadze Porati, brain world models propose our four-dimensional spacetime exists as a brain embedded in higher dimensional space. Gravity propagates in extra dimensions at very large distances, weakening its effective strength and producing accelerating expansion. These models predict specific deviations from general relativity testable through gravitational wave observations and cosmological structure formation. Chameleon field models introduce scalar fields that couple to matter with strengths depending on local density. In high-density regions like the solar system, the field acquires large mass, making it short-range and evading solar system tests. In low-density cosmic voids, the field becomes light and long-range, affecting cosmological evolution. This chameleon mechanism allows strong coupling driving acceleration cosmologically, while remaining consistent with local gravity tests. Anthropic selection provides different approach, arguing that the cosmological constants observed value, while requiring extreme fine-tuning from fundamental physics perspective, becomes expected if observers can only exist in universes with appropriate dark energy density. Universes with much larger cosmological constants expand too rapidly for structure formation, while those with negative constants recollapse before stars form. The string theory landscape, containing perhaps 10 to 500 different vacuum states with different cosmological constants, might allow anthropic selection. Most universes would have inappropriate constants preventing observer formation, but the tiny fraction with suitable values would include our universe. This explanation requires accepting eternal inflation and multiverse, philosophical positions some find problematic. Observational tests distinguish among dark energy models through multiple probes. The expansion history, mapping through distance redshift relations, constrains WZ, the equation of state parameters evolution with redshift. Different models predict different WZ trajectories, distinguishable with sufficient precision. Structure formation provides complementary constraints. Dark energy affects matter clustering growth rates as its density becomes significant. Models with W1 or with dark energy, dark matter coupling predict different clustering evolution than LCDM. Large-scale structure surveys measuring galaxy clustering and weak gravitational lensing constrain these effects. Integrated Sachs-Wolf effect, correlations between late-time matter clustering and cosmic microwave background temperature fluctuations, probes dark energy's gravitational effects. As photons traverse large-scale structures, they experience gravitational redshifts and blue shifts from changing potentials if dark energy affects structure evolution. Measuring correlations between CMB and galaxy positions tests dark energy models. Gravitational waves from merging black holes or neutron stars propagate through expanding space, accumulating phase shifts depending on expansion history. Future observations of many mergers across redshift ranges could constrain dark energy through gravitational wave cosmology, independent of electromagnetic distance indicators. Observations combining multiple probes strengthen constraints by breaking parameter degeneracies. Supernovae alone cannot distinguish between dark energy equation of state and spatial curvature. Adding CMB and BAO measurements separates these parameters. Including structure formation data constrains modification of gravity theories versus pure dark energy scenarios. Current data favor simple cosmological constant over quintessence and modified gravity, but uncertainties remain large enough that alternatives cannot be excluded. As observational precision improves, model parameter space narrows. Some alternatives may be ruled out while others remain viable until observations achieve precision required for definitive tests. The theoretical landscape remains rich with possibilities, each representing attempts to explain cosmic acceleration through physical mechanisms more satisfying than unexplained cosmological constant. Whether nature chooses simple constant vacuum energy, dynamical quintessence field, modified gravity, or something more exotic, remains to be determined through observations. Understanding the range of alternatives contextualizes the cosmological constant problem and highlights how different mechanisms produce observationally distinguishable predictions. Future observations might reveal which, if any, of these scenarios describes reality. Measuring cosmic distances. Determining accurate distances to astronomical objects represents one of observational cosmology's fundamental challenges. The cosmic distance ladder employs multiple overlapping techniques, each calibrated against closer methods and extending to progressively greater distances. Webb's observations improve several rungs of this ladder, providing more precise distance measurements that constrain cosmic expansion history and dark energy properties. Geometric parallax, the apparent shift in nearby star positions against distant background as Earth orbits the Sun, provides the most direct distance measurements. The parallax angle in arcseconds relates to distance in parsecs through the simple relationship AD × 1p, where p represents parallax angle. The European Space Agency's Gaia satellite measures parallaxes for billions of stars to micro-arc-second precision, mapping distances throughout the Milky Way to hundreds or thousands of parsecs. Cepheid variable stars serve as the next ladder rung, extending distance measurements to tens of millions of parsecs. Cepheids pulsate with periods from days to months, with longer periods corresponding to higher intrinsic luminosities through the Leavitt period luminosity relation. Measuring pulsation period determines absolute magnitude, which compared to apparent magnitude yields distance through the distance modulus equation. Webb observes Cepheids in galaxies hosting recent Type Ia supernovae, calibrating supernova luminosities by determining host galaxy distances. NIRCam's infrared observations penetrate dust that obscures visible light, reducing extinction corrections needed for accurate photometry. Individual Cepheids become detectable to distances approaching 100 million light-years, extending the range where this technique provides precise calibrations. The tip of the red giant branch, TRGB, offers an alternative to Cepheids less affected by metallicity variations. Red giant stars reach maximum luminosity at specific absolute magnitude MI4 in the near-infrared I band when helium flash ignites in their cores. This discontinuity in color magnitude diagrams provides a standard candle with intrinsic scatter below 0.1 magnitudes. Webb's sharp imaging resolves individual stars in TRGB measurements to greater distances than Hubble, potentially reaching 200 million light-years for bright red giants. NIRCam observations in near-infrared bands detect the TRGB feature clearly, measuring distances to supernova host galaxies through independent technique cross-checking Cepheid results and testing for systematic differences. Type Ia supernovae, standardized through light curve, shape, luminosity correlations, extend distance measurements to billions of light-years. After correction using stretch and color parameters, these supernovae serve as standardizable candles with absolute magnitudes MB 19.3 in blue wavelengths. Webb observes supernovae in infrared reducing dust extinction corrections and potentially revealing intrinsic variations invisible in optical wavelengths. Surface brightness fluctuations in elliptical galaxies measure distances through variance in pixel-to-pixel brightness stemming from Poisson statistics of resolved stars. Nearby galaxies show larger fluctuations from individual bright stars, while distant galaxies, smooth as stars, blend together. The fluctuation amplitude at fixed wavelength indicates distance. Webb's infrared observations, where old giant stars dominate, enable SBF measurements to hundreds of millions of light-years. Gravitational lensing provides geometric distance measurements independent of standard candles. Strong lensing producing multiple images of background sources constrains lens mass distribution. Time delays between images of variable sources like quasars depend on both lens geometry and distances to lens and source. Measuring delays plus lens modeling yields distance ratios constraining cosmological parameters. Baryon acoustic oscillations imprint characteristic scale in galaxy distributions from sound waves in the early universe. This standard ruler of approximately 150 megaparsecs provides distance measurements through comparing physical scale to angular scale. Webb spectroscopy determining galaxy redshifts enables BAO measurements at high redshifts where previous surveys lacked sensitivity. The cosmic distance ladder's power lies in redundancy. Multiple techniques overlap, allowing cross-checks for systematic errors. Cepheids and TRGB both measure distances to supernova hosts. Agreement validates both methods, while discrepancies reveal potential problems. Combining measurements improves precision beyond individual techniques through weighted averaging accounting for uncertainties. Systematic uncertainties affect each technique differently. Dust extinction impacts optical observations more than infrared, motivating Webb's wavelength coverage. Metallicity variations affect Cepheid period luminosity relations at 0.2 magnitude level, though corrections exist. TRGB depends on helium abundance and age. Supernova standardization assumes similar explosion physics across cosmic time. The Hubble tension, approximately 9% disagreement between local and early universe H-Wuzhou measurements, might originate from distance ladder systematics. Cool measurements use Cepheids and supernovae calibrated through nearby parallaxes. CMB measurements assume LCDM cosmology fitting observed acoustic peak structure. If either approach contains unrecognized systematics, apparent tension might resolve. Webb observations address potential systematics through independent measurements. Infrared Cepheid observations reduce extinction uncertainties compared to optical. TRGB provides alternative calibration to supernovae. Multiple techniques measuring same distances test consistency. Early Webb results show distances agreeing with local ladder supporting H073 km/s MPC, though analysis continues. Photometric redshifts estimated from galaxy colors in multiple filters provide lower precision redshifts for objects too faint for spectroscopy. Machine learning algorithms trained on spectroscopic samples predict redshifts from photometry, achieving scatter DZ 1 pleats 0.02 to 0.05. Webb's JWST Advanced Deep Extragalactic Survey obtains both photometry and spectroscopy, improving photo-Z calibrations for high redshift samples. Spectroscopic redshifts from emission or absorption line measurements provide precision, typically day 0.021 or better. NER Spec's multi-object spectrograph observes hundreds of galaxies simultaneously through micro-shutter array, obtaining redshifts across wide fields efficiently. High spectroscopic completeness reduces biases from preferentially missing certain galaxy types. Distance measurements combined with redshifts constrain cosmological parameters through the distance-redshift relation. For flat universe with dark energy, luminosity distance dl relates to redshift through integral over expansion history involving hz, an equation of state wz. Measuring dlz for multiple redshifts constrains h0, matter density OLM, and dark energy properties. Statistical analysis employs likelihood methods comparing observed distances to predictions from various cosmological models. The best fit parameters maximize likelihood or equivalently minimize H2 quantifying disagreement between data and models. Confidence regions determined through H2 contours indicate parameter uncertainties, accounting for measurement errors. Systematic uncertainties require careful treatment beyond statistical errors. Correlated systematics affecting all supernovae in similar ways cannot be reduced by increasing sample size. Examples include calibration uncertainties, dust corrections, potential evolution of supernova properties. Statistical and systematic errors combine in quadrature for total uncertainties. Future observations will improve distance measurements through larger samples, extended redshift coverage, and multiple independent techniques. The Vera Rubin Observatory will discover thousands of supernovae, Roman Space Telescope will observe infrared light curves, and Webb will provide host galaxy distances through Cepheids and TRGB. Combined datasets should constrain dark energy properties to percent-level precision. Understanding distance measurement techniques and uncertainties establishes how observations constrain theoretical models. Precise distances across cosmic time map expansion history, revealing whether dark energy remains constant or evolves, and whether phantom energy threatens eventual cosmic destruction.